Okay, we are the Smart Grid Group. We're Chris Bastian, Logan Robertson, and Kriston Wilson. Thanks, Dr. Hengren, for taking the time to visit with us today. We really enjoyed this project. Basically, what we were given is we needed to meet both the heating and the electric demands of a population. We had a nuclear reactor that we were given. We also had a wind farm that could provide intermittent wind energy. And we were given, we didn't know what kind of battery, so we just assumed it was a lot of small batteries that we were given to store this energy so that we could meet the electric demand. This is, right here is what we were given to start with, the Simulink model. You can see the battery over here, and then also we have the intermittent wind, the nuclear power plant, and then these are our demands. And to meet both the heating and the electric demand, we had to run the nuclear power plant almost at maximum capacity the entire time because we needed more heat at night when it was cold and we needed electricity during the day. And so without a way to really store this heat, we either needed a lot of electricity or we needed a lot of heat. So there was significant waste. 300 megawatt hours of power was wasted, and then there's also a lot of heat that was wasted.
Okay. So for us to make the system more efficient, we added 3 different things to the Simulink model so that we could be able to meet our demands for our heating and for electric. The first thing that we added was we added this heat storage device, and the way that works is that when the heat would be able to be stored in a certain medium, which could be stored easily and then be extracted easily when it's needed. The second thing we added was we added this logic function right here. And the idea with this is actually after we've been watching and what happens during the day and the patterns that were happening, we're able to decide on certain set points that we could set our battery for storing electricity and also our heat storage system. And with this, what this does is electricity would come in here, and we'd want to fill up our battery so we can meet all our electrical needs. And then once our battery was full, then they'd send the electricity up through this heat pump right here, which takes the electricity, multiplies it by 3, and turns it into 3 more times heat. And then we'd be able to either store that or use it, since the heat was the one that we had the biggest problem with meeting. The third thing that we did was we added 2 PI controllers right here. And these PI controllers are able to look at which system, either our heat or electrical system, which one needed more attention, and depending on which one needed more attention would give that PI controller control over our nuclear power plant, and would be able to ramp it up so it would be able to meet the needs of our heating and our electrical. And with these PI controllers, we also did the IMC tuning method, and then we adjusted it to meet our needs or our expectations for the system of what we wanted.
All right, and so with those implementations, these are the results that we were able to achieve. As Logan mentioned before, with the original model, in order to meet our demand, we had significant amounts of energy wasted. We had around 300 megawatts of electricity wasted and megawatt hours of electricity wasted, and around 900 megawatt hours of heat wasted. After we implemented our changes, we were able to reduce those amounts significantly. We ended up having around 90 megawatt hours of electricity wasted in our controlled model, and around 50 megawatt hours of heat wasted. And those values are primarily due to losses in our efficiency of charging the battery and heat storage. And then also we varied the demand curves as well as the wind supply to see how our model would perform under different conditions, and we were able to keep the improvements well below what the original model provided. The electricity ended up with a maximum of around 115 megawatt hours wasted, and the heat stayed at about 50 megawatt hours of wasted heat. And these results we wouldn't have been able to achieve without implementing our heat storage in order to meet our heat demand, as well as having the logic function to determine what we do with our excess electricity, and then finally our PI controllers to manipulate our nuclear reactor.
Any questions?